Okay, so we can get started. I think we have some due dates coming up for the projects next week. Um, I'm not a super stickler on the time, but try to meet the deadline. If you don't meet the deadline, let me know. I want a firm time on when you're going to hand stuff in so that it doesn't drag out till the end and you get punished with this class and all your other courses. But I would like to see you get it in on time. Okay, so last week we were talking about explosive eruptions. I'm hoping we can finish up today on that chapter and then move on to lava flows. So I'm going to try to use this diagram. I don't know if this is going to work to try to illustrate some of the things we were talking about last week. So last week we kind of looked at the anatomy of an explosive eruption from the chamber all the way up to the stratosphere. So obviously we can't see beneath the surface, but I'm going to try to draw it right here. So here we go. This goes down into the volcano, some depth. Not terrible. All right, so at some level in the chamber, let's say right about here, that is something called the solubility surface. Everything below that, there's too much pressure for bubbles to form. So all the volatiles are still in solution in the magma. But at some point, as you get closer to surface, there's going to be less pressure, and bubbles are finally going to form when you have a little less pressure. At that point, the concentration of volatiles dissolved in the melt reaches the solubility, and they start coming out of solution. You start getting lots of little bubbles. And as you go up higher in the chamber, less pressure, more time for the volatiles to rise. At some point, you're going to reach a place where you're going to have about 75 to 78 or so percent bubbles. At that point, the bubble walls are so thin, it's essentially inflated to a foam. And at that point, the magma begins to break, and that's called the fragmentation surface. That's where it starts breaking apart, and then all those gases that are released will start jetting the broken pieces of foam upward. And as you get closer to the surface, there's less and less material above it. At some point, you are going to perhaps, it doesn't happen in all eruptions, go from subsonic speeds, slower than the speed of sound, to supersonic speeds, faster than the speed of sound. So somewhere between 600 and 700 miles an hour. It's really fast. So stuff's coming out faster than a jet engine. So it's getting blasted out of the vent of the volcano at rapid speeds. And in this photo, you can actually see some things happening. You see this sort of really tight column right above the vent. That is called the gas thrust region. In other words, it's being blasted up by gases. It's really not any different than shooting a bullet out of a rifle, being blasted out by gases. But at some point, the gas is not going to be able to keep lifting the material higher. There's two things it can do. It can fall back to Earth, or if the cloud is sufficiently dilute, there's pieces of ash in here because the pumice fragments have been banging together at 600-700 miles an hour. So it just gets all fragmented up into little pieces of ash. It starts ingesting air from the outside. It's ridiculously hot. That means it's really low density. Even though there's pieces of rock inside, because the gases are so expanded because it's so hot, it will rise buoyantly. So this is what we call the convective thrust region. It's going to rise just because it's less dense than its surroundings. It's hotter than its surroundings, but it'll keep rising. Now, what happens in the stratosphere, down here in the troposphere, as you go up, temperatures get colder in the atmosphere. So things, if that was the way all the way up to space, this stuff should just rise to space. But what happens in the stratosphere is that temperatures start warming. And at some point, you get warm eruption cloud against warm air, and the density is the same. And at this point, it starts to mushroom out. So you get mushrooming right beneath the stratosphere. So this is up where jets fly. And all this is in slides from last week. I just want to use it as a springboard for what we're going to do tonight. And then remember, this stuff can't stay airborne permanently. I mean, these little chunks of ash are heavier than the surrounding air, so they will start falling out. The biggest stuff will fall out closer to the vent, and as you get farther away, you'll get fine material, sometimes miles, tens of miles out. So this pumice fall and ash fall tends to be really well sorted for an eruption. You get all big stuff near the volcano. You get farther away, you get all fine stuff. So ash and pumice that fall out of these tall eruption clouds tend to make really well-sorted deposits. I'm going to show you lots of slides of actual deposits in the field. So that's kind of the process with some visuals. You guys have any questions? Okay. That's what ashfall looks like from Plinian columns. You see lots of layers here. Those are just different ash layers, different compositions of ash. This stuff right here, probably rhyolitic ash, maybe some andesitic ash here, more rhyolite there, more andesite there, rhyolite, andesite, rhyolite, andesite, rhyolite, multiple events producing this stuff. And if you look close, you can see this deposit, all that stuff's about the same size. You don't see much bigger pieces. You don't see lots of fine pieces. So when I'm talking about Plinian fall deposits, airfall deposits, pumice fall deposits, ashfall, stuff falling out of the air from eruption clouds, they tend to be really well sorted. You'll see that's really different than some of the other explosive products. So what I'll give you is kind of a checklist of things that you would look for to say, oh, this is from this type of eruption. This is from another type of eruption. So Plinian fall deposits are really well sorted. If you were farther away from the volcano than this photo here on the right, you'd see much smaller pieces. Get smaller and smaller until you're miles away. It'd just be really, really fine ash. And remember, this stuff is falling out of the sky sort of one grain at a time. So it's not terribly compacted, very well sorted. This is from a volcano in Ecuador. And one thing about these fall deposits is they blanket the topography. They mantle the topography. They're just as thick on top of hills as they are in valley because it's just falling out of the sky. And because they're big deposits, you don't see much of a change in thickness unless you look at it over a really big area. So in a single deposit like this, you're going to see really regular, equal thickness beds that are really well sorted. You can see here the lower part, you were forming some beds, and then you had some erosion that changed the topography, and then you get stuff on top that drape that topography. So what you have here are a series of eruptions over a pretty long time period where the topography was somehow altered. I don't know what actually changed the topography here. Some sort of slow erosion over time, I'm guessing, but I don't know that for sure. That lower set may have all been from a single eruption cycle that maybe had lots of different Plinian columns go up over a certain time, and then could have been 1,000 years where you had erosion and then another set falling. The other thing that's really interesting about some Plinian eruptions is that these Plinian eruptions go, but every once in a while they're punctuated by even bigger blasts that sort of throw material that's much bigger than what it had been throwing out all at one time. And you get these large bombs that can be tossed miles, and they land on the pumice and ash beds and just sort of auger their way in. They're really pretty impressive. You can see these have landed on the ash and have deformed it. And it works even better if the ash is a little wet, because it starts to act more like a plastic layer. And you can do some simple physics and say, oh, we have this rock here, it's these dimensions, has this density, it weighs this much. How much energy was required for the volcano to actually throw this thing, whatever distance this is away? If you've had physics, you probably looked at equations for ballistics, for parabolic movement of material in response to gravity. You simply apply those to some of these bombs, and you can calculate the energy of the eruption. These are called bomb sags, and they're actually pretty common in these fall deposits. That's a particularly good one. Now, as this material is thrown up in the air, if it doesn't go up very high, that means it goes up and falls back to Earth really quickly, and it doesn't have much of a chance to lose heat. If you think about the Hawaiian type of eruption, where you have kind of a curtain of fire with low columns, this stuff only goes up 1,000 feet or so, compared to Clinian eruptions, which can go up 100,000 feet. So it doesn't have much time to cool. So when it lands with an awful lot of heat. And what can happen sometimes is they can have enough heat that they sort of recongeal on the ground. You get big blobs of material coming out of a Hawaiian type eruption. It goes up red, it comes back red, lands on the ground, splatters, other stuff splatters with it, and they all sort of congeal together. And then they can start moving downhill under gravity, just like a lava flow. That's called agglutination. It's real common with Hawaiian type eruptions. It can happen with ash eruptions, but not typically from the ones that produce high columns, because that material goes way up, loses lots of heat. Pieces are really small, so they don't have much heat to begin with. They fall back to Earth, and they're just not hot enough to congeal back together. But if you get a pyroclastic flow, and we'll talk about how pyroclastic flows form here in a minute, sometimes they can keep enough heat that they congeal back together, and that's called welding. And the resulting rock is called a welded tuff. A tuff is an ashy layer. Welded means that it was hot enough to sort of fuse its way back together. And sometimes, once they fuse back together, they can flow too. And that's called rheomorphism. Flow after fall, if you think of it that way. So stuff is actually an explosive product, but at the end, it ends up flowing downhill, and you see flow structures and flow banding. Really hard to tell the difference between a rheomorphic ash deposit and a lava flow. There's stuff in Idaho that you can't tell if it's rhyolitic lava flows or rheomorphic tuff. Because essentially, once they're on the ground and doing the same thing, they look the same. Now, from an eruption history standpoint, it's kind of important to know which, because a lava flow eruption requires much different conditions than a big ash flow producing eruption. But yet the products can look really similar after, and it gets you can get lots of arguments about which is which. So again, the rheomorphism, it's flow after the explosive material retains enough heat, congeals itself together, agglutinates, and then moves downhill under gravity. So agglutination is just sort of the refusing of explosive products and rheomorphism, as if those fused products can move downhill under gravity as a flow. Okay, any questions? All right, so up in the upper left corner is spatter. That's an explosive product. It's, I talk about fluids being broken. Most people don't think of fluids breaking. You think of fluids flowing. If you get enough gas, you can tear a fluid apart and it break it. And that's what's happening in the upper left. That's Hawaii. So that stuff goes up. In this case, it's probably going to go up 15 or 20 feet, come right back down. Hasn't had much chance to lose heat. They're big globs. They sort of splatter together, and then they can start moving. So coming together, that's the agglutination. Rheomorphism is once they start flowing. This bottom one, there's some flows in Idaho. You can see sort of the thick eroded beds. When you look at them, you see flow banding and all these cool structures that you typically get in lava flows. But most people think they're actually rheomorphic tuffs. So they're welded tuffs that were flowing down these steep slopes. It's really difficult sometimes to tell them apart, and it really sort of confounds and confuses the eruptive history of these volcanoes. You don't know just how many lava flow producing eruptions it's had, how many ash flow. It'd be really difficult to decipher it. And you can get your eruption history wrong if you don't. Okay, so those were all products coming out of eruption columns, okay? Columns that go up, material that comes back down. Now we're going to talk about stuff that moves downhill under gravity. And these are called pyroclastic flows. Some volcanologists call them pyroclastic density currents. This is a photo from Mount Unzen in Japan, which erupted in 1991. You can see this cloud that's kind of hugging the ground. That is the fine ash that's being carried upward by the heat given off of the moving pyroclastic flow. And it's fine ash from lots of rocks colliding that you don't see in here because they're inside the flow. It's basically a big avalanche of material. All these rocks are banging together, getting progressively smaller, chipping off really fine pieces that then sort of elutriate upward. But the very base of this is a super dense rock avalanche. So I'm always fond of saying that if you get stuck in these things, you die. It's very quick, and it's a combination of being vaporized and pulverized to death at exactly the same time. It's a very quick, unpleasant way to go. You only feel it for half a second, and you're gone. So pyroclastic flows, or pyroclastic density currents, as a flow has pretty high density, it's an avalanche, so it's rocks, but it moves as a mass sort of downhill. So it has high, what we call particle concentrations, just lots of blocks and pieces, and extremely hot, right around melting temperatures. And it has a basal avalanche that you really don't see in this. And then it has a less dense, we call this the surge, that's not as dense, and that's the actual cloud that you see there. So you usually just see the surge part of a pyroclastic flow. So you get the dilute, which is just really fine ash, gases from the flow, and any air that might be ingested by the cloud as it moves across the surface. And then at the base, you have this rumbling, pounding block avalanche. And what a lot of us find really, really strange, and I've been around these things a few times, is that they're silent. You don't hear anything. And yet there's this tremendous avalanche with all these rock fragments banging into one another. And it's like, okay, where's the sound going? Well, One thing is that the air is really hot, so sound travels differently in super hot air. And there's a guy, in fact, he just passed away last week. He was a geophysicist from the University of Arizona, Jay Malash. And he's always contended that the other thing about these pyroclastic flows is they go a lot farther than a normal avalanche would. And he has this idea called fluid acoustic. Let me think if I can get this. The fluid acoustics model. Basically, the flow is absorbing the sound and it's sort of going downhill on a layer of sound. He's got all these hairy equations. So basically, all this banging together produces sound waves. Sound waves echo off the ground, and then all this stuff sort of rides on this layer of sound. Some people don't buy it. It's super creative, so I love it. I love wild ideas like that. But it sort of explains why they go so far and why you don't hear these damn things, because it's actually being absorbed by the flow. So, kind of interesting. Like I've said a few times, that's really why I really like volcanology, because inside these things is a really different world. It's a hot, strange world that we don't come in contact with really out here. Because it's an avalanche, flow, the basal avalanche, will take the steepest path downward. It will be controlled by topography. Basically, they hug river valleys. Now, the surge is dilute, and it can be rising buoyantly, and sometimes it'll actually detach from the flow. You can have a flow and the surge coupled together and it's going downhill, and then the topography, the river valley, takes a hard left. The basal avalanche will take a hard left. It'll probably ramp up on the side and move down. The surge just might keep going straight. And then the flow, as it goes a different way, will create a new surge. So you have this surge that goes straight, and then the pyroclastic flow will continue to bang together, and it'll make another surge. And then if it turns that way, that surge may go straight too. So these surges do weird things. Now, if you get caught in a surge, you're not going to get pulverized to death, but you are going to vaporize if you're in the thick of it. If you're on the very edge, you might survive with some terrible burns. A few people have survived these, but I'm not sure they want to. Yeah, these are not things you want to hang around. Again, the surge can detach from the flow, and I think I'm going to show a video at the break where you can actually see this. It's from Montserrat. Montserrat is an island in the Caribbean that's been erupting, oh my gosh, maybe 20 years now. I think it started in 1995, so that might be closer to 25 years now. And it built a really huge lava dome that is continually collapsing. It's growing, 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 and then pieces slough off and create these pyroclastic flows that go all the way down to the ocean. And it's made a huge delta of pyroclastic material. And then every time a new flow comes down, it goes over the delta, the avalanche plunges into the sea, but the surge goes scooting across the top of the ocean water, just right out to sea. And I've got some video of it. It's really impressive. And there's been reports of surge clouds taking out ships that were just moored offshore. So not always a good thing, but something you should be aware of. So this is not a great diagram, but it sort of shows the two parts. So this is the avalanche down here, and then this is the surge up there. The surge is, again, it's basically a cloud with dust in it, ground up rock fragments, ash. So this is an ash cloud, and the ash is super fine, usually sand size or smaller. Down here, this is blocks. They can be big, giant blocks, they can be baby head blocks, they can be everything in between. And as they roll down, they break into smaller and smaller blocks. Sometimes they break so small that they produce ash, and the ash is then carried up by the hot air, and it makes this really cool surge. So we're going to talk about various ways that pyroclastic flows can form in a minute, but there's different types of pyroclastic flows. We have pyroclastic flows that are made primarily of just pumice and ash. So that avalanche would actually be pieces of pumice. Now you know how light pumice is, but if you get hit with a piece of pumice traveling 150 miles an hour, it's going to leave a mark. You're not going to survive that any better than you'll survive a dense rock coming at that. It's like your comment a couple of weeks ago with the hard hat. At some point, it just doesn't matter. They're just so powerful that there's not much that we can do to withstand them. So the pumice and ash flows, we'll talk about how they form in a couple minutes. Basically, they're from collapse of eruption columns, Plinian columns. Sometimes Plinian columns cannot sustain their upward movement and they collapse. And all that material comes crashing back down to Earth as one big mass. And then it flows down the side of the hills really rapidly. It's really an impressive thing to see. And then a lot of pyroclastic flows are what we call block and ash flows. These result typically from dome collapse. So you've got this lava, it's really dense, but it usually is sitting on the top of a volcano, too steep, and it just breaks off, rolls down the hill as an avalanche, and the pieces get broken up. So one is an avalanche of pumice, and the other is an avalanche of basically dome rock, lava flow. So real dense versus real vesiculated. So this is what a pyroclastic flow deposit looks like. First of all, unlike pumice fall deposits, they don't drape the landscape. They don't mantle the landscape. They're confined to river valleys. And because it's either pumice or dome rock, it's banging into other pieces of pumice or other pieces of dome rock. You still have some big fragments in the avalanche. You get lots of ground up stuff. So it tends to be just the opposite of a fall deposit, very poorly sorted. You can see here, you got big chunks, you got little chunks. This would be confined to probably a river valley area. So it looks very different in the field. So instead of mantling the topography, they tend to be really thick in valleys and pretty much non-existent on the tops of ridges. We're going to look at surges in a minute, and surges have really cool bed forms, just like a lot of sedimentary structures. They have cross bedding, they have ripples. But this stuff is just an avalanche, it's a mass. So you don't see any internal bed forms. You just see a wedge of poorly sorted, either broken dome rock or pumice. Again, the poor sorting really separates it out from any ashfall. Both ashfall and pyroclastic flows could be made of pumice. But in the case of the airfall, very well sorted, mantles the topography. With the pyroclastic flows, very poorly sorted and just confined to the river valley. Because it doesn't go very high up into the air, we'll talk about how these things can form. It tends to retain a lot of its heat. So these can be really hot. So if it goes through a forest, it'll be hot enough to scorch trees and plants. So you tend to get a lot of charcoal in here, which is great because you can do carbon-14 dating if it's an older deposit. I had you guys watch the Mount Pinatubo video a few years ago. That's how they figured out that Mount Pinatubo erupted very infrequently, is that they fished out a bunch of charred wood deposits out of the pyroclastic flows. And we're able to look back and it's like, this was 1,000 years ago, this is 2,000 years ago. And you can start to come up with a periodicity on the eruption. So because it retains a lot of its heat, it not only scorches any life form that might be present, but if it's big enough, the stuff can weld back together and then flow rheomorphically. That's not common, but in the really big pyroclastic flow deposits that you get with calderas. In those eruptions, it's pretty common. Okay, give you a sec to, I would write down the 6 ways they form, and then you can sort of either do your own sketches, or we'll go through these one at a time. I'll let you get the main categories down first. Okay, so we'll just sort of walk through these slowly. The diagrams are kind of tiny, but I think you'll be able to figure out what's going on. So if we look up at A, okay, what you have in A is a single pulse column. If you think back to our type eruptions from a few weeks ago, one of the types we talked about was the Vulcanian style, which is kind of a single really high intensity blast that can throw material pretty high up in the air. But it's not sustained. It's just a blast that might go on for a couple of minutes. And what typically happens is the material goes up, but there's not enough gas to sustain its blast real high into the atmosphere. You might go a mile or two up, but then all that material before it gets to the base of the stratosphere, or even to the sort of convective region of the eruption column that we talked earlier, doesn't have quite enough gas to do that. So the material falls back to Earth as a big mass. So the column essentially collapses. And then that material starts rolling down the side of the hill. Now, some of the smallest particles of ash may stay up above and get carried away in the wind and then fall out on top of this deposit. But for the most part, everything but the finest material goes up, falls back down, and races down the side of the volcano. But it's a single blast, so it typically does not have a lot of volume to it. Of all the pyroclastic flows here, it's probably going to be the smallest deposit. It's probably going to go the shortest distance. But you still don't want to be caught inside of these because they're super hot, and it's still an avalanche where material's moving. I've seen pyroclastic flows move as slow as 60 miles an hour. I've seen them move 200 or 300 miles an hour. Even 60 mile an hour, you don't want a 5-inch piece of pumice in the face that's going 60 miles an hour. One piece won't kill you, but if you got hit by 300 pieces simultaneously, probably not going to fare very well. The second one sustained column collapse. This tends to happen during Plinian eruptions, so a nice long several hour eruption where you have a sustained column. But some things can happen in the column and in the vent to cause the column to periodically collapse and send down pyroclastic flows. What will happen is the beginning of a Plinian eruption makes that beautiful column like I showed at the very beginning of class. But remember, stuff is coming out of there sometimes supersonic speeds. And if you think about a volcanic vent, the edges are rock, right? And think about volcanic rock being jetted through that at 700 miles an hour. It's going to start eroding. Sometimes it starts augering out that vent. So the vent gets wider. You guys have all done the hose thing, right? Where you turn on the hose, and if you want the stuff to go faster and farther, you put your thumb over, right? And that, what it does is it restricts the opening, right? What happens if you enlarge the opening? So think about this. So at first you have a kind of a tiny, tight column. What happens if suddenly you get a big bunch that sloughs off the sides of the vent and opens it up? It's not going to be able to go up as high, right? So that material then just sort of loses its velocity before it gets up too high. It comes pouring back down to Earth and makes these pyroclastic flows. So what you'll see sometimes is then the lighter material still gets carried away. You get the big anvil-shaped mushroom cloud. But the lower part of the column might start collapsing, especially the bigger pieces. You can get situations where the fine stuff has enough, is light enough so that the gases can carry it to the upper part of the atmosphere, but the bigger pieces just sort of boil over, roll down the side of the hill. So as the eruption starts to lose its juice, the Plinian eruption, you might start getting lots of these, where there's just not enough gas to sustain the column, and it'll repeatedly collapse. And then once pyroclastic flow comes to rest, the stuff that gets carried up in the column will fall out on top of it. So it's not uncommon to see a pyroclastic flow deposit covered by ashfall, and it'll all be the same material. The third one is kind of a case like the second one, but in the case of the third one, there's never enough gas thrust to get stuff to go up very high. It just sort of bubbles out. It fragments, but there's just not enough gas, or the vent is too wide, and it just can't, there's just not enough force inside the vent to throw this material up very, very high. So it just boils out, sort of bubbles over the vent and then goes rolling down the hill. Now you'd have an almost impossible time telling the difference between deposits formed by B and C. The only difference is you might get a little ashfall in between pyroclastic flows with B. The fourth one is really rare, lateral blast. I know of 2 volcanoes that have had this. One was witnessed, one was not. One that was witnessed was Mount St. Helens, the big blast from 1980. And then it was after the St. Helens blast that volcanologists looked back at another eruption in Kamchatka at a volcano called Bezmiany that happened in the 1950s. It's got an amphitheater just like St. Helens. It's got a dome just like St. Helens. It had deposits just like St. Helens, but it wasn't witnessed. Somebody knew exactly how that formed. Lateral blasts tend to result from unloading, from landslides that come off the volcano and expose the magma chamber, and it rapidly expands to basically to ash right away. Just sort of, it's like shaking up a soda pop and pulling the top, sprays everywhere. St. Helens, ash cloud moves 600 miles an hour to a distance of over 18 miles. But it doesn't really have the basal avalanche. So it's simply, for the most part, a surge. There's no dense stuff. Stuff expands so rapidly that you don't get many big pieces in it. It really is an ash flow. And it hugs the ground, but sort of. It'll follow the topography a little, but it'll hop over ridges and mountains as well. E is a dome collapse. This is what killed all the people at Mont Pelée. Basically, you have a lava dome forming at the summit. It gets oversteepened. Small chunks can come off and form little pyroclastic flows. Sometimes huge sections come off and form really big pyroclastic flows. This is what killed Maurice and Katja Kraft, my friend Harry, and 41 other reporters at Mount Unzen in 1991. It's really common at Mount Merapi in Indonesia. Mount Merapi's had a dome growing for decades, sends down pyroclastic flows every day, but 1 million people live on the volcano. And sometimes people get killed. Then this last one's really rare. It's when you have pyroclastic flow deposits that are laid down by an eruption, but then they, for some reason, get oversteepened too, and then they collapse. So it's kind of a recollapse of a pyroclastic flow. It's an avalanche from an avalanche. So the first pyroclastic flow comes down as an avalanche, comes the rest, maybe the front of it's on a steep overhang or something, and eventually it slips down and forms another pyroclastic flow. But these are pretty rare. All right, take a few minute break. I'm gonna queue up a video that we'll watch and then move on with the rest of it.